In this module, we're going to look at ancient Mesohaline settings for which there is no same-scale counterpart. It follows on from part 1, where we looked at those organic enriched Mesohaline settings where we have good one-for-one comparisons between modern and ancient counterparts. Before we start, let's just have a look at the world's oil distribution and production. In other words, where does it all come from? This plot from the US Energy Information Administration plots production over the past few decades, showing how Saudi Arabia has maintained its position throughout much of the 30-year history as the dominant producer of hydrocarbons. And much of the oil coming out of that system comes from Mesohaline source rocks, for which there is no same-scale equivalent. The other thing to note in this chart is the fact that since about the mid-2000s, the Russians have come to produce a little bit more in terms of equivalent oil than Saudi Arabia. And in the last 3 or 4 years, the US has become the prime producer of crude oil, related in large part to the production from hydrofractured, carbonate-prone oil shales. And we'll have a look at these examples of a couple of these carbonate-prone oil shales in Mesohaline settings a little later in this module. Let's go back and remind ourselves, what do we mean when we talk about a hydrocarbon source rock? Well, hydrocarbon source rocks are typically finer grained carbonates or siliciclastic mudstones. Quite often they're laminated, that contain sufficient oil and gas prone organic material that upon burial and heating can generate and release enough liquids to form commercial accumulations of oil and gas. And not all source rocks are Mesohaline. Some are set in anoxic normal marine upper slope settings, and here's an example of the Shublik Formation from the Upper Triassic of Alaska, and you can see quite clearly its laminated nature. This was formed in a normal open marine setting in what was an anoxic bottom. But we are going to focus in on carbonate source rocks. And if we look at the distribution of source rocks over time, we can see that there's a common factor here, and that common factor is basin restriction, stagnant circulation or anoxia. Both of these factors contribute to the deposition of large areas of oil and gas prone source rocks. And this can be in both siliciclastic and in carbonate settings. The common factor in most of these systems across the Phanerozoic is quiescent anoxic bottom conditions. And because they are anoxic, there's little bioturbation, and so we tend to preserve laminated, relatively dark coloured, organic enriched sediments. And this is true of both what we're going to focus on, the anoxic Mesohaline carbonate mudstones, and also the anoxic aluminosilicate black terrigenous shales and marls. And we can see that there are 6 major intervals where source rocks have produced significant volumes of hydrocarbons, and together those 6 constitute the source for more than 90% of the world's discovered reserves of oil and gas. And those 6 periods are starting from the base of the column, are the Silurian, which generated about 9% of the world's reserves, the Upper Devonian, about 8% of the world's reserves, the Pennsylvanian to Lower Permian, about 8% of the world's reserves, the Upper Jurassic, which has produced about 25% of the world's reserves, the Middle Cretaceous, some 29% of the world's reserves, and the Oligocene to Miocene, producing some 13% of the world's reserves. So what this chart clearly shows is there are particular settings and particular times in the past which are more prone to allow organic enriched sediments to accumulate. And these periods are typically associated with periods of marine anoxia or with highly restricted basinal settings where anoxia develops on the floor of those sumps. If we look at the depositional associations within those accumulations, And here we're looking at an oil source systems by definition that have generated more than 500 million barrels of oil. We can see that the marine dominates the majority of the world's source rock depositional settings across the Phanerozoic. There are also some deep marine anoxic settings, as well as lacustrine and deltaic settings. We're going to focus in on this marine association in mesohaline settings for source rocks. But I must emphasize at the start, this is not the only setting in which hydrocarbons can be generated. However, the mesohaline anoxic bottom setting does dominate much of the source rock systems in the Middle East and other evaporite associated systems. There are a number of reasons for this. Evaporitic settings tend to be prone to stratification and mass water mixing, and periods of flooding and freshening where, in a combination of ongoing sunlight, enhanced nutrient supply, and influxes of freshening into the system, we see feast or famine associations in the depositional setting. And it's that pulsing production which will tend to swamp the efficiency of the decomposers that would otherwise consume the organic material. That organic matter that's produced in those near surface waters then has to pass through the gauntlet of consumers, of periodic oxidation, and if we have relatively slow burial rates, the biota will tend to consume and biotomate those sediments. And so we tend to have, as well as production, another secondary set of factors which tend to destroy the organic material. The mesohaline setting, this pulsing production, can overcome all three of those factors to allow significant volumes of organic matter to reach the floor of the depositional system. And that floor is typically anoxic. And then we have an additional set of factors which we have to look at in terms of how we get the organic material into the subsurface. If we have rapid sedimentation, and that can be clastic influx, it can be biogenic production, and it can be evaporite production. If we have elevated levels of sediment input across any three of those groupings, we can dilute the organic content and so destroy that rock's ability to act as an efficient source rock. We also have to consider it in terms of ongoing accommodation space for the sediment residing in long-term anoxic environments, facilitating the burial and preservation of that organic material. And of course, we know that in the depositional setting that's mesohaline, we tend to see long-term brine layering, long-term bottom anoxia or dysoxia, all of which tend to facilitate and encourage the deposition and then preservation of the organics in that potential source rock. If we look at the two general environments where in the marine realm we tend to form organic enriched material, the fact that we have a restricted basin sump with stratified or stagnant anoxic base to that sump will tend to preserve the high levels of organic material that's descending as a rain from that upper oxic marine environment into that anoxic bottom. And this is the typical scenario that we see in many mesohaline settings as we pass from the marine into the non-marine, or as we pass from the non-marine into the marine-fed evaporite systems. Both of those scenarios will tend to give us situations where we set up this anoxic, typically more saline bottom water that facilitates the preservation of the organic material that's being produced in the upper parts of that brine mass or water column. And also the fact that in the hypersaline setting we tend to see schizohaline upper water, so we have this feast and famine pulsing taking place in that upper water mass, will tend to feed pulses of sediment into that anoxic bottom below that anoxic brine layer. And so we find oil-prone type 1 and type 2 systems being preserved in the kerogens under normal marine situations, we tend to find that we have significant and efficient bioturbation and consumption of the organic matter. And so what we tend to find is that we only get oxidized organic matter, the non-source type 4 organic matter, accumulating on the floor of that system. Unless we move to zones of upwelling, which is what we saw in that Triassic example from the North Slope of Alaska, where we have sufficient production, high levels of production, sufficient to create an ongoing rain of organic material to the bottom, and so facilitate disaerobic, anaerobic conditions on the bottom. And so we then move to a more type 2, type 3 style of organic preservation in that system. So we can have organic matter accumulating not in restricted environments, but in normal marine environments, if we can also set up scenarios where we have upwelling and large volumes of organic matter then reaching and being preserved on that anoxic bottom, typically in an outer shelf, upper slope environment. Within the Mesohaline realm, this is the typical hydrological layering that we see facilitating the preservation of high levels of type 1, type 2 organic material on the basin floor. We have a photic zone, which may be also subject to schizohaline fluctuations in salinity and a periodic pulsing of organics reaching the bottom. And we have a long-term ongoing more saline water mass where we have anoxia dominating those bottom conditions. And so across the Phanerozoic, the general observation that we make is that the destruction of organic matter is much less efficient in anoxic sediment, which are typical of subaqueous brine-layered or mesohaline brine-layered depositional systems. And in those systems, the pulsing that we see associated with it can swamp the efficiency of the decomposers. Clearly, across the broad range of bottom settings in mesohaline, marine-fed, lacustrine, and shellfish upwelling scenarios, anoxia is the prime control in the creation of a source rock. Anoxia typically sets up conditions where the bioturbators are no longer active, because bioturbation is typically tied to the activity of multicellular life. Multicellular life does not deal well with low levels of oxygen, nor does it deal well with synchronous elevated salinities. And so in many anoxic mesohaline settings, we do not see bioturbation of the bottom sediments. And in many mesohaline settings, we also see that the brine layering creates a scenario where the anoxic-oxic contact is actually above the sedimentation surface, and we have hydrogen sulfide rich bottom brines in the system, all of which tend to decrease the efficiency of the decomposition process and so enhance the level of organic matter accumulation in those bottom sediments. This chart plots the effects of anoxia. You could also think of it as plotting out the effects of increasing salinity, which is tied to anoxia, as we go from the left to the right in this chart. Under anoxic conditions, sediments tend to be laminated. We see preservation of elevated levels of organic material. In scenarios where there's an iron source, we will see the build-up of early diagenetic pyrite in the lamanites, the organic rich lamanites. And we'll also see significant increases in the preservation of the biomarkers tied to that anoxic bottom brine. Multicellular life, which is responsible for the much of the bioturbation, does not do well in anoxic hypersaline conditions, and there tends not to be a well-developed epiformer, as we would otherwise see on the bottom of normal marine sedimentation. We tend to see microbial mats more common in anoxic settings, both from the activities of the cyanobacteria and the archaea. We tend not to see licitotrophic larvae in that environment, nor do we tend to see the planktonotrophic larvae in that environment. The only life that we see there is typically the microbial decomposers that are better adapted to conditions of anoxia and increased salinity. In summary, when we look at organic matter preservation, across the broad spectrum of marine and marine-fed mesohaline settings, preservation of elevated levels of organics is facilitated by high rates of pulsing organic supply, relatively low levels of organic consumption in those anoxic bottom brines, and the preservation of that material being encouraged or facilitated by long-term bottom anoxia or dysoxia above the sedimentation surface. And so with that in mind, let's now look at where do organic rich sediments accumulate in the Phanerozoic. Well, we saw in the previous module how closed seafloor depressions, deep hypersaline anoxic lakes atop salt allochthon or autochthon provinces tends to accumulate organic material. We also saw how the instability of that environment means that these accumulations tend to be local scale and have a relatively low preservation potential compared to the other mesohaline settings we're going to discuss. The other system that we looked at in the previous module with same-scale modern and ancient counterparts was the underfilled mesohaline lacustrine setting, where comparisons were made between African Rift Valley lakes and ancient similar successions, for example, in the Green River Formation. The other 4 examples that we're looking at of mesohaline source rocks are all examples where we do not see same-scale modern and ancient counterparts. They encompass basin centre lacustrine sumps in opening Sin Rift restricted phase succession with a sub-sea level base to the succession and a marine-fed evaporitic drawdown hydrology. And these typify incipient oceanic basin-wide salts. Then we have the sub-sea level foreland deep marine-fed collision belt basins with both basin-wide and intracratonic associations, and the intrasalt freshening stages during saline giant infill of a sump with once again both basin-wide and intracratonic successions. And then finally, the platform mesohaline intrashelf and intracratonic lows top relatively shallow water evaporitic shelves and and this latter setting typifies much of the source rock deposition in the Mesozoic of the Middle East. None of these 4s have same-scale modern counterparts. They are all typified by long-term stratified brine columns and productivity exemplified by long-term feast and famine. Given that ancient saline mesohaline systems are typified by brine stratification and bottom anoxia across the saline lacustrine, evaporitic platform and basin-wide evaporite settings, let's remind ourselves of how these systems form, what characterises their hydrologies, and why they are developed on such broad scales that have no modern-day same-scale counterparts. Within the marine realm, both the marine-fed platform and basin-wide geosystems are characterised by the sub-sea level sump hydrology, which facilitates marine seepage into the succession. And they also form in particular tectonic associations. This is a plot of the aerial extent of the ancient basin-wide lacustrine and saline evaporitic platform successions compared to saline quaternary environments. And as you can clearly see, with the exception of the ancient lacustrine associations, both basin-wide and platform successions have evaporitic extents an order of magnitude greater than what we see in both marine and non-marine evaporite successions of the quaternary. You can refer back to the relevant modules on depositional and geological controls of platform and basin-wide settings for the detail on these associations. For now, let's just summarise the significant features of these systems, ranging across a depositional spectrum, which is much broader than anything we see today. So here are the 2 end members of this ancient evaporitic succession, for which we have no modern-day counterpart. Platform evaporite succession, where we have extensive, typically subaqueous evaporite beds separating normal to restricted marine platform carbonates, versus the basin-wide evaporite association, when whole basins oceanic basins typically went evaporitic, and we form these very thick and broad associations of evaporites. Platform evaporites typify greenhouse mode climate and the associated greenhouse eustacy, times when we did not have the high amplitude, high frequency fluctuations that we see in our current ice age or in past icehouse mode climatic associations. The basin-wide settings have particular tectonic associations. They typify transition from a continental to a full oceanic marine stage, so they tend to typify incipient ocean basins as the rift is opening up to become increasingly marine, or they typify soft suture collision belts as the marine realm passes up section into non-marine associations typified by the collision of continent-to-continent proximal plates. Generally within this association, the Mesohaline source rock accumulation is defined to that transition in and out of the main marine-fed evaporite stage in both the platform and the basin-wide successions. Because in both of those scenarios, it is that transition going into increasingly hypersaline or increasingly continental from the marine realm situations where we facilitate the setup of sufficient restriction to allow bottom brines and anoxia to develop. Generally, we find that our Mesohaline source rocks are proximal to or adjacent to our main evaporite phase in the system. In the platform mode, we tend to see a succession where we have a series of intracratonic or pericratonic seaways that, as they go into the evaporitic phase, develop locally anoxic, relatively shallow water hypersaline sumps. And once again, I refer you back to the earlier module where we talked about the hydrology of the platform evaporites and the eustacy of a platform evaporites in detail. For now, we'll accept that this system shows increasingly saline transitioning up into hypersaline conditions as the connection with the open ocean is cut off via typically sedimentation or tectonic uplift in a greenhouse mode rather than an icehouse mode eustatic association. For the basin-wide successions, we are looking at successions where we are either at the incipient oceanic stage, as we are opening a rift and we see marine waters coming into what was previously a continental association, or we have a continent-continent suturing association where we see increasing restriction of the marine waters as we pass into a continental association with closure of the oceanic basin. And of course, as we discussed in detail, this relates back to the tectonic positions within the Wilson cycle, whereby in the context of Mesohaline source rock, our Mesohaline source rocks tend to form in transitions into or out of the main evaporite stage. So this is typically in the Wilson cycle, later stage B or stage E to F in the opening rift, or in the closing continent-continent suture belt. We can also have locally intracontinental lacustrine sag basin forming across a broad spectrum of tectonic associations. So within the Wilson cycle, we tend to see continent-continent proximity associated with the formation of Mesohaline source rocks. And this can either be in the opening phase B, where we find Mesohaline lacustrines generally situated below the main evaporite stage, or in the proximal stage prior to the evaporite phase as the closing basin, the remnant basin, becomes increasingly evaporitic. It passes first through a Mesohaline phase and then into the full evaporite phase. Both of these situations are what we call craton edge or continent-continent proximity evaporite associations, where the Mesohaline subaqueous basin sets up the required density stratified, brine layered, anoxic stagnant conditions that facilitate the accumulation and the preservation of our organic rich sediments within the framework of the Wilson cycle. So let's have a look at just quickly as a couple of examples that we discussed in more detail in earlier modules to remind ourselves of the types of basins where these Mesohaline associations will form in basin-wide evaporite associations. all examples of what we call plate edge sumps, where we have continent proximity. And so here, for example, is the mid-Jurassic, the Calovian in the Gulf of Mexico, immediately prior to the deposition of the Luan salt. And likewise, we have the rifting association between South America and Pangaea in the Aptian. As we open up the basin, we pass from a initially continental association in this pre-Atlantic sag basin. Then we form a marine-fed, basin-wide, incipient oceanic evaporite succession in a sub-sea level setting. And then we open up in both of these realms into normal marine, non-mesohaline deposition. So in the rifting association, which are these both examples of, we are transitioning from the continental into the marine. And so if we look at the typical types of geology we develop in those situations, we typically develop an extensional margin with continental sediments that becomes increasingly mesohaline as we develop a marine influx sag basin stage where we form thick evaporites. And below that, we have the mesohaline source rocks. And then at the level of the evaporites, we have seal in that succession. So this is an example from the Santos Basin of offshore Brazil. You could draw very similar conclusions to the Luan salts in the Gulf of Mexico as well, where we have this evaporite thick unit overlying our mesohaline lacustrine to marine feed phase that immediately precedes the formation of our thick rift evaporite succession. Here we have the late Neoproterozoic phase, the Hormuz formation, where we form significant and extensive evaporites across the Middle East at the level of the Cambrian-Precambrian boundary, which is interpreted as a collision belt transition as we go from the marine of the Neoproterozoic up into the non-marine sedimentation of the lower Paleozoic in this association. Then we have the Zechstein. Examples would include the pre-Caspian basin-wide evaporites in the Urals foredeep, or the Zechstein basin-wide evaporites in the Pangaean, in this case in what is probably an intercontinental sag basin. But once again, it sets up a similar scenario whereby we have a widespread evaporite succession acting as a seal to the underlying mesohaline source rocks. If we put it in the broader framework of basin wides and plate edges, there are three general positionings that we see where our evaporites will form. We form them on the continental edge in a opening passive margin scenario at the incipient ocean stage. We form them on the continental edge during the subduction phase as we close the oceanic basin. And then within the continental or intracratonic interior, we can also have a series of relatively shallow water sag basins, which are periodically evaporitic, once again with mesohaline source rocks preceding the main evaporite stage or post-dating the main evaporite stages in these basins. So let's just focus in on the intracratonic for a moment and look at what happens within intracratonic basins. Unlike the basin edge scenario, these occur on top cratonic material, sialic material, and what we tend to see is a longer term stacking of a number of saline, non-saline, marine typically episodes. We can stack a whole series of these things, 5 or more third order evaporite carbonate cycles in these successions. And what distinguishes the continent edge from the intracratonic is that we have a much longer time frame in the intracratonic setting where the system hovers around sea level, and we see these transitions in and out of the saline normal marine scenario. And so we get a whole series of generally shoaling upwards marine cycles, often capped by evaporites, very similar to what we see in platform evaporite successions. And it can be quite difficult to separate out intracratonic from platform evaporite successions in terms of the sedimentary features in these basins. And it's really the regional basinal architecture, as we see in seismic, which allows this separation between intracratonic sag basins and platform evaporite basins. Sometimes we consider intracratonic basins as a subset of basin-wide deposits. Other times we see them as being filled with stack cycles very similar to what we see in platform evaporites. What contrasts the intercratonic sag basins from the basin-wide evaporite associations is that the cratonic edge basins, be they extensional or collisional, have much thicker salt successions in them and much shorter active saline phases compared to the intercratonic associations. And the hydrography that's driving a intercratonic evaporite phase tends to be related to failed rift situations or a lockogen. And in general, it includes zones where we've got intercratonic asthenospheric downwelling, creating, via isostatic response, a accommodation space on the continental surface, which we then see filling with a whole range of sediments. And as I said, this tends to be a long-term, tens of million years type basin versus the much shorter term, millions of years basins we see on the cratonic edge. And so we see isostatic responses and sedimentation in intercratonic associations, which are thinner but much longer term. And so the deposition tends to be within an intercratonic setting related to much gentler topographic expressions with a relatively low subsidence and the occasional marine ingress into this association, which gives us the subsea level seepage hydrology setting up the evaporite associations within the intercratonic setting. I'll refer you back to the earlier module which focused in on intercratonic evaporites for more detail, but recognise that there are three basic settings in which Mesohaline source rocks form in the ancient, for which there are no modern day counterparts. And they are the basin centre incipient oceanic basin, the transition into evaporites of a collision soft suture belt association, and this can have implications in terms of both basin-wide and intercratonic sedimentary sags, the intrasalt freshening stages forming organic rich intervals sandwiched within thick salt in both basin-wide and intercratonic settings, and then finally, and perhaps most importantly, the evaporitic platform association that typifies many epiric seaway saline evaporitic source rock successions. These systems are characterized by long-term stratified brine columns and by pulsing feast or famine biotal responses, creating conditions which facilitate the preservation of laminated, organic rich source rocks. In the next part of this module, we will look specifically at a range of examples in both basin-wide associations, intercratonic associations, and then in the platform evaporite associations.